I want to do a quick little test to measure how fast this little guy is moving. So I'm going to set up, see if we can figure out some way to connect this caliper here and make some measurements. So let's see what we can come up with. All right, I think this is going to work here. If I put this between these and zero it out, then as it pushes it closed, it should give us the distance that it's traveling. So let's see, zeroed out. All right, let me change the code, make sure that we're moving in the direction we want to go. Let's see, move back, motor 1. Moving back is moving that way, so we don't want to do that. So let's get rid of that, and let's do move. Motor 1, this many equals 100. This much equals 2500. That just sets the speed. Let's do a quick test, make sure we're doing what I think we're doing. Okay, maybe let's print where we are as well. Uncomment those. Okay, so that's working. Then we can go back. Whoa. That's a new one. Huh. Don't press that combination. I don't know what I just did. This Raspberry Pi 4 just, like, really got excited. I tried to do Control-Shift down. Which is like a shortcut. And I have somehow completely killed the Pi, so let's restart it and see if we can fix this. That's really funny. That was definitely a first for me. All right, do not use normal keyboard shortcuts in Thonny on the Raspberry Pi 4 OS. That's the lesson that we've just learned. Okay, we might be back, although I did nervously show the other look there for a second. See if we can connect. We're connected. It's still doing that thinking thing. I don't like the thinking. F5 is working, but okay, we're done spinning. All right, so definitely don't try to do the move align thing in Thonny, which is actually a pretty good example of why I am looking to set up where I can do this using any text editor. But let's comment this one out. Let's move back, get back to where we want to start. So that's 100. We can do, let's try 400. That sound you're hearing is this little thing right here going up and down. Move back. We are going to test with 100 steps and see what that distance is now. And we have the calipers set. And we are zeroing. Make sure they're roughly parallel. Let's see. I guess you can't quite see that. Let me move the camera a bit. All right, here we go. Okay, I've got 3.92 millimeters the first try. 4.22 millimeters the second try. 4.22 the third try. 4.23 the fourth try. 4.24 the fifth try. All right, this is already way more accurate than I was expecting. We're within what, one or 2 hundredths of a millimeter after 100 steps. Let's do a little bit of math quick and see what we're looking at. So let's see, 4.24 millimeters per 100. So 4.24 divided by 100, 0.0424. Say 0.0422 if we're going with the averages. So 4.22 divided by 100. We should be looking at 0.0422 steps per millimeter. So let's add a variable up here and let's call it steps, or millimeters per step equals 0.422. And then we can use that variable. So we can do a little helper function. We can call it millimeters to steps, and we pass in millimeters, and then we're going to go steps equals millimeters times, if my math's totally wrong, then the cool thing with programming is that I'll run it and it won't work, and then we'll fix it. Millimeters per step. Print steps. It's always a great way to do this for starting out, is print it instead of running it. Less of a chance to break things. And then we can just call this function millimeter to steps. And if we put in 4.24, or 4.22 rather, hopefully this is going to print 100. Printed 1.78, see, so my math was obviously way wrong. Let's see, okay. Steps equals millimeters times millimeters per step. That's obviously wrong. We want to divide that. That gets us 10, which means I probably missed a 0 up here. I did, so we add the 0, and that gets us 100. Woohoo! All right, now you know why I love programming. You can kind of just play with it until you get it right. So now if we want to, we can use this function in our call here, and we'll test it with the calipers here in a second. So let's go, instead of print, we want to return the value so we can use it, and then move. I guess let's move back quick. Get to the starting point. And while it's doing that, I am going to say, I'm going to do, I guess, a move millimeters. Motor. And in here, it's going to say steps equals millimeters to steps. Millimeters. And then we could do millimeters, motor, direction. So we can go if direction same as, let's do 1, and we'll default to 1. Direction is the same as 1, move, motor, this many equals steps. This much equals speed. And we'll put speed equals 2500. Again, I'm using variables here just so that sorry, I'm using variables here so that I can overwrite that if I want to, but I can make this function call with fewer values. Just makes it, it's kind of a convenience thing. And it's nice to have defaults because it's a simple way to document functions. All right, LF direction is -1, move back, motor, this many equals steps, this much equals speed, else print direction not need to ask for directions. Not a very helpful print statement, but it's kind of a fun one. And now we can try this out. So let's comment out what we had, and we can move those down there. And let's say move millimeters 100. And we'll set motor equals motor1 as another, just a default helper. So now move millimeters 100. Let's just see if it works first. Oh, you know, I probably should have thought about how far 100 millimeters is, right? That might have been a good idea. I think this is a 400, maybe 400 millimeters. I'm not really good with millimeters. Hoping it stops soon. Are we to the end? Yowzer, that's a lot. Getting nervous, getting nervous, getting nervous. About to demonstrate the reason for a limit switch. All right, I did a keyboard interrupt. Couldn't handle it. 100 millimeters is probably pretty far. Let's move back 20 millimeters. So we're gonna set the direction equal to -1, which will tell us if that part's working. It is, nice. Let's see what 20 millimeters is. 25.4 should be an inch. There we go. All right, so I think we would have been fine, but we also might not have been fine. So let's move, I guess, a couple inches. Oh. Ba-da-bum-bum-bum. I mean, couple. I use couple a little bit, what's the word? Not literally, I guess. Almost there. Almost there. Here we go. Here we go. Okay. All right, so now we can start our test, and we can see if our calculations were right. So we are going to 0 this, and we're going to say move 10 millimeters the other direction. .77. Let's try it again because we probably have quite a bit of not squareness going on here. Oh, here we go. I can hold this up to the here, let me take. Does it have to have that in there? No, that's the lock. Right, don't need the lock. All right, so now we can rest this more so at those guys. The problem with calipers, if they're not square, then they're not true. All right, we're going to do the first one. I'm going to leave it in that position. We're going to do another one. So 9.65. Running it again. So hopefully any of the play got taken out of it. 9.93. That's nice. We're within 7/100ths. Another one here. Ooh, look at that. That is a thing of beauty. 10.01. Oh, you're a little bit out of focus, aren't you? Look at that. That's nice. So it's not necessarily every time, but it's pretty good. Let's see, how can we, let's go the other way with this. So let's go a little bit farther, and then let's put this up here. And we'll hook that little guy in there. That little guy in there. Oh, this is a good one. Yeah. Here, if you want a closer view, let me move you a little bit closer. I know it's exciting. Okay. We're still recording? Yeah, we are. All right, here we go. Get our lighting on there so you can see it good. Ready? Change our direction. So direction is -1. 10 millimeters. Testing now. .79. Not loving it. I do feel a little wiggle right when it starts. 19.82. $29.85. All right, so after 4 tests, we're 1/10 of a millimeter off, which is, let's see, 1/10 of a millimeter in inches would be 0.1. Times 25.4. No, that'd be 2.54. So 0.1 divided by 25.4. Oh wow, that's like 3/1000ths of an inch. Okay, never mind. I'm no longer complaining. I'm now ecstatic. Still within that 10th. Okay, let's go the other direction and let's pick a number. Let's say 85. See if we can hit it. Do I have 85? Yeah, I don't quite have 85 ready. So let's do 15 more in -1 direction. Make sure we don't run out here. Oh, it's looking good. Okay, there we go. Can I get you a better lighting on there? Ooh, that's nice lighting, right? Yeah, that's good. All right, let's do it like this. So, 64.97. We should probably go a little further. All right, we're gonna go 85. I'm gonna zero it out. Ooh, look at that. We ended our 8th one. 2/100ths of a millimeter off. All right, here we go. We are going to, let's see. What's our best way here? I guess we can go back and then try it the other way. Should we do that? All right, we're going to do a kind of sloppy one here. 85 millimeters. And go. You know, you could hook one of these calibers up to, oh, sorry, your light's off. You could hook one of these calibers up to where you're reading the values from it. It could be kind of a fun way to get a really exact positioning device. 60, 65, 70, 75, 80, 84.83. So after 85 millimeters, we are 0.17 millimeters off. And if my math is moderately okay, 0.17 divided by 25.4 is 7/1000ths of an inch. 7/1000ths of an inch after 85 millimeters. That's actually a lot more accurate than I was expecting. But let's go the other way, because this is kind of fun. And let's see how that goes. Now, this time, oh, getting a phone call, hang on. All right, I've just got a few minutes or like a few seconds left to finish this up. So, but the one thing I was about to say is, let's do where well, first let's get it all the way. Let's get it as close to the end as we can. So let's do a little 5 millimeter, 5 millimeter, 5 millimeter. We can do another one, 5 millimeter. Okay. And it's panic inducing not having any stop blocks. And now we will set this here, like so. Get a nice angle for you to be able to see. Get it nice, as parallel as I reasonably can right now. That's pretty good. Zero that out. Let's set this at 30 millimeters. And actually, you know what? We're going to start by going 1 millimeter, and that's just to make sure that everything like slack's taken up. Okay, so now we're going to go 30. 0. And view's good. Yep, you can see well. Let's do it. Oh, did you see that? It was 0.8. Look at that. 0.8 in 30 millimeters. That's crazy. So 0.8 would be 0.08 divided by 25.4, 3/1000ths of an inch. So roughly 2/1000ths of an inch per inch. Speaking of inches, let's go back to the beginning and try this again. But this time, let's do a fun inch conversion thing. So we'll switch to inches on here. And then we will move 25.4 inches. 25.4 direction is -1, which for whatever reason up is -1. This is going to be the last shot of the night, so then I will be publishing this video. Zero it out. Let's move our little 1 millimeter. Check sure everything is right. Okay, we're good. 25.4. 0. Correct me in the comments if my 25.4 math is wrong. And here we go. This should be 1 inch. Let's see it. Come on, halfway there. 3/4. Oh, you gotta be kidding me. Do you see that? We are 1.0035. So just confirmation that it is within, oh, it moved a smidge, but that it's within 3.5 thousandths per inch, which is less than 1/128th because it moved. Let's get it back there. Oh, back to inches there. What's that say? Yeah, I mean, it literally rounds it and just basically says it's an inch. So, cool. Well, that was my quick little distance test for the open slider. We wrote some code. We looked at some numbers. And I'm honestly really, really excited. I had no idea that would be within 3/1000ths per inch right out of the gate. So, yeah, that's actually, I'm getting really excited about this because then I can start thinking about how that translates into milliliters and lots of other applications that I will, as of yet, not name. But thanks for watching. Catch you again on the next update.